Hello everyone, my name is Yuzhong Wu, and I am a PhD candidate in the Chinese University of Hong Kong. In this video, I'm going to present you my paper in DCASE 2020 workshop, searching for efficient network architectures for acoustic scene classification. So the highlights of this paper is as follows. In this paper, we propose a simple and effective random search policy to obtain high accuracy convolutional neural network architectures under strict model size constraint. So using this search policy, we can automatically discover the optimal trade-off between model depth and width. And we use several efficient convolutional modules to build our models. And to save the search time, we limit the search space and we use some tricks for fast evaluation of the candidate architectures. And the found CM models give higher accuracy compared to an AlexNet CM benchmark, which has a very large model complexity. We are dealing with the task of acoustic scene classification. It is the task of classifying a recorded audio signal into one of the predefined acoustic environment classes. In this study, we focus on three-class acoustic scene classification problems. And the three classes are indoor, outdoor, and transportation. And in this task, we require the model size to be smaller than 500 kilobytes. So here is an overview of the acoustic scene classification systems with three scene classes. So here we have three input audio signals, and each audio signal is analyzed by the acoustic scene classification system. It gives the prediction of the acoustic scene classes. So the first audio signal is predicted as outdoor, second is predicted as indoor, and the third one is predicted as transportation. Before we introduce our search policy, I would like to first introduce some background about neural architecture search. NAS is a technique for automating the design of deep neural networks. For the search strategies, usually exhaustive search is impossible when the search space is extremely large. Thus, many search strategies were investigated using the reinforcement learning. For example, Baker et al. Proposed the meta-QNN, so whose searching is based on Q-learning, and Dov and Lee proposed to use the recurrent neural network to generate network architecture description, and the RN is trained by reinforcement learning. The time consumption of the above NAS algorithm is still very large, and it can be further reduced by, for example, Pham et al. Proposed the efficient NAS with parameter sharing. It searches for optimal subgraph within a predefined large computational graph. Stamoulis et al. Suggests that the search space can be further reduced from multipass to single pass. Meanwhile, Yu et al. Reported that a random architecture selection policy might have similar performance with the NAS search strategies. So since our task is dealing with low complexity acoustic classification system, we also need to build models with efficient architectures. So models pursuing high accuracy usually have large model complexity, such as the AlexNet and the ResNet. To apply CNs for mobile and embedded applications, many efficient network architectures are proposed. In this study, we mainly look at mobile nets and shuffle nets. So for ShuffleNet version 1, the core idea is to factorize the original convolution operation into a depthwise convolution and a pointwise convolution. And then the version 2 of mobile nets further improves the efficiency by using inverted residual structure. For ShuffleNet, it utilized the idea of channel shuffle and pointwise group convolution. So in ShuffleNet version 2, it further improves the accuracy by introducing the concept of channel split. Notice that the above models are proposed for computer vision tasks, so fine-tuning is needed to better suit the task of acoustic scene classification. So we use two convolutional modules to build our classification systems. The first module is called the Depthwise Separable Convolution, or shortly as DSC. DSC is the core module of MobileNet version 1. It is factorized version of the standard convolution operation. The standard convolution operation usually have a kernel size of 3 times 3 times n, where n is the number of kernels. And the DSC is composed of 2 successive operations. The first is the depthwise convolution, and the second one is pointwise convolution. And through this factorization, the model parameters and computation costs are reduced to a large extent. Another efficient module we used is the inverted residual with linear bottleneck. This module is the basic building block of MobileNet version 2. The term inverted residual means the residual connection exists between the narrow part of the network. The residual connection improves the gradient flow and enables effective training of deeper networks. And the procedures of the inverted residual module is also very simple. The first step is to expand the low dimensional feature into high dimension using a pointwise convolution, and then apply filtering by depthwise convolution, and then project it back to low dimension using another pointwise convolution. Instead of using the original DSC and inverted residual modules, we'll change them a little bit by replacing the ReLU activation with the switch activation function, because it was reported that switch performs better than ReLU in various applications. And we can regard switch as a smooth version of ReLU. The equation of switch is x multiplied with the sigmod of beta x, where beta can be a constant or trainable parameter. And for simplicity here, we just set beta equals 1. In this figure, the left part is the DSC module used in our models, and the right part is the inverted residual with linear bottleneck modules for our network architecture sampling. So here's an example of the sampled model architectures. The sampled architectures has 4 convolutional blocks, each having 2 modules and 1 pooling layer. And the modules can be identity mapping. The model B is a DSC module. So for the modules to be selected, we provide 5 choices listed in this table. And the reason we provide 3 times 3 and 5 times 5 convolution kernel size is to enable more flexibility in receptive field. The identity mapping is just a dummy module used to increase the diversity of sampled networks depth. Here is the description of our research space. For each configuration item, every possible choice has equal probability of being chosen. For each configuration, we chose one of the options, and then we form a candidate model architecture. So first, we will decide the number of blocks, means the convolutional blocks from 2 to 4. And then we decide number of output filters in stem convolution layer from 4 to 128. And the growth ratio of filter number means after each block, the growth of the filter numbers. For example, if we have 1.0, it means that the model has a constant number of filters for each convolutional layers. If the ratio is 2.0, it means that after each convolutional block, the number of convolution kernel is doubled. And then for each block, we select the module A, module B, and the type of pooling layers by random selection. So the search scheme is that first, we randomly sample an architecture from the search space, as mentioned in the previous slide, and then we check the model size. If the model size is too small or too large, that is, it is not in the range of 250 KB to 500 KB, we will discard it and we will repeat the first step, which is random sample architecture. And then if the model size requirement is satisfied, we train the model for only 3 epochs for fast evaluation. So after evaluating a considerable number of models, the ones with highest test set accuracy or lowest test loss are chosen. And then they are trained with the sufficient epochs, say 60, for final evaluation of the performance. So the data set used in our experiments is the TAU Urban Acoustic Scene 2023 class deployment dataset. It contains 3 acoustic scenes: indoor, outdoor, and transportation. And the audios are recorded by a single recording device in binaural 24-bit format. The training set contains 25.5 hours of audios, and the test set contains 11.6 hours of audio. And the input feature we use is the wavelet-based filter bank feature. And we calculate the average and difference of the scaleogram between left and right channels. And then we cut it into segments with 128 time frames, representing 1.28 seconds of audio. And then the final feature segment shape is 128 and 128. This is the input shape of our CEM models. We randomly sampled 510 distinct candidate architectures. The evaluation result is as follows. 510 distinct candidate architectures are sampled and evaluated. And as we can see, the model size is in the range of 250 to 500 kilobytes. And we can see most of the models lies in the accuracy range of 92%, from 92% to 94%. And we also have some models with a higher accuracy. For example, this model have a 95% accuracy. Evaluation of a candidate model takes 20 minutes using single GPU. So evaluation of the 510 models takes about 1 week using single GPU. We also plot the accuracy distribution of candidate models with different growth ratio of filter number. So in this figure, the x-axis is the candidate model accuracy. The y-axis is the normalized count of models lying in the accuracy range. So if we calculate the mean accuracy for different growth ratio, we can have this table. As we can see that as the growth ratio increase, the mean accuracy is decreasing. The model with constant number of filters in each convolution block has the highest mean accuracy. The reason could be because we only have 3 output classes, so it is sufficient to classify them using embedding features with small dimension. So here is the model we found. The model A has the highest validation accuracy, and the model B has the lowest validation loss. Notice that the model B has the growth ratio of filter number being 1. So we compare the performance of different model architectures. We used a manually designed high complexity model as the benchmark, and then we test the mobile nets and shuffle nets designed for vision applications. And then we evaluate the performance of our model A and model B. As we can see that the mobile nets and shuffle nets can preserve most of the accuracy compared to the large complexity model. And our model A and model B even outperforms the manually designed high complexity model. And then changing the data type of parameters in trained model A or model B from float 32 to 16 does not affect the accuracy. In this paper, we propose a simple yet effective random search policy to find high-performing lightweight models for acoustic scene classification. And our best-performing model achieves an accuracy of 95.8%, with the model size being only 150 kilobytes. And we also observe that the CEMs with constant number of filters in each convolutional layer perform better in this 3-class acoustic scene classification problem. And this work may serve as a baseline for further study on NAS algorithms in acoustic scene classification tasks. So this is the end of the presentation. Thank you for listening.